Hi guys, and welcome to a new lesson. This lesson is about migrating to an SQL database, and we are going to look at our Lendy database, the tool hire application that we are trying to work on. And before getting into the nitty-gritty, we need to see how Python and SQL come together. So accessing SQL from Python, SQLite provides an application programming interface, or API as it is called, consisting of a number of standard functions that allow programmers to perform all the same operations that we have been doing without using the interactive SQL prompt. The SQLite API is written in C, but wrappers have been provided for other languages, including Python. Python has similar interfaces to many other databases, and they all provide a standard set of functions and provide very similar functionality. This interface is called the Python DB API, and its existence makes porting data between databases much easier than if each database had its own interface. The DB API defines a couple of useful conceptual objects that form the core of the interface. These are connections and cursors. And using SQL connections, a connection is the conduit between your application code and the database's SQL engine. The name comes from the client-server architecture used by most SQL databases, whereby the client must connect to the server over a network. For SQLite, the connection is actually to the data file via the SQLite library. The arguments passed to create the connection are of necessity database specific. For example, many databases require a user ID and password, and some require IP addresses and ports, whereas SQLite just requires a file name, like in the example we are shown here. So connect, in here you usually put the path of the database where it is located, and if I'm working in the current directory, then I just put the name of the database. If I've started SQLite prompt from the same directory that I'm working in, then I can use it this way. And once a connection has been established, you can go on to create cursors, which are the mechanism used to issue SQL commands and retrieve and receive their output. In principle, you can have more than one cursor per connection, but in practice that is rarely needed. So using a cursor when accessing a database from within a program, one important consideration is how to access the many rows of data potentially returned by a select statement without running out of memory. The answer is to use what is known as SQL as a cursor. A cursor is a Python iterator, so it can be accessed iteratively, one row at a time. Thus, by selecting data into a cursor and using the cursor methods to extract the results, either as a list for smaller volumes of data or row by row, you can process large collections of data. So let's try that out now. So we are going to try to use the Python DB API. Just exit from here, clear the screen. So we'll use the SQLite 3 module to create a table populated with data and perform some queries with select. We will then delete the data, drop the tables, and exit. So let's try this exercise right now. So start up the Python interpreter and import SQLite 3. Make a connection to a database. I'll explain at the end what I'm doing. Let's add another value. Let's add another value. Let me print out what we inserted. So as you can see, the cursor returns a list of tuples. This is very similar to what we started off with back in the comma separated values in section 2. And you could simply use this list in your program as if you had read it from a file, using the database merely as a persistence mechanism. However, the real power of the database lies in its ability to perform sophisticated queries using select. So let's try out a few queries during doing the following example. Let's try our function. And let's try to do some data manipulation commands. So what did we do here? So let's explain that. We started by importing the SQLite module. The next step was to create a connection to the database file, which in this case was memory indicating that you wanted a temporary database held in the computer's memory. You then created a cursor object that you subsequently used for all the SQL interactions. We created a test table and inserted 3 records. We then used the select star idiom to extract all the data from the table. We then used the fetch all method of the cursors to view the output as a list of tuples. Other options include using fetch one within a loop or fetch many to return batches of results. The next step involved defining a Python function that used a string to locate records of interest. This demonstrates how Python functions can be created to hide the details of the SQL from the user. You use this technique later to create an API for the lending library application of the tool hire application. Having shown that the function works, we deleted the records, dropped the tables, and closed the cursor. We then executed a connection commit method that permanently applies any changes we have made, followed by a closing the database connection itself. The use of the commit is slightly complex with the DB API, sometimes calling commit for you, and at other times we need to do it explicitly. As a general rule, you should always call commit before closing the database connection. In this example, it makes no real difference because the database exists only in memory and disappears whenever you close the connection. If you are using a file-based database, you need the commit to ensure your changes are visible next time you open the database. So that was some examples, quick examples for working with SQL and Python. Now we're going to try to create the LendyDB SQL database from the our tool hire application. The database design is not significantly different from its previous incarnations. We just have to translate it into SQL syntax and add in some constraints to improve data integrity. The initial database setup is usually easiest to do using raw SQL commands, as we did in the earlier sections, although it is possible to do it all from Python. Occasionally another tool is better suited to the task at hand. So one note is that if you don't have the SQLite interpreter installed, you can still execute a SQL script using the execute script method of the cursor object. This method takes an SQL script as an argument. The script can be read from a file or a standard Python string, which could be a multi-line triple quoted string. Note that you need to terminate the SQL statements with semicolon, just as we did when using the SQLite interpreter. So to build the database, we need you can use the LendyDB SQL file, which has all the SQL statements for creating the tables. And before we use this file, you can open this file and have a look at it. To look at the contents of this file. So in this file, we need to drop all the tables at the top of the script, and the order is important because otherwise the referential constraints fail and an error results. Notice also that we use the numeric type for the item price because this caters for both integer and floating point values. It also means we don't need to worry about those pesky dollar signs that we had to strip off in the previous incarnations of the data. Apart from the various key fields, the other fields are all declared as text. So in order to create our database, we first need to create a database. Let's call it Lendy.db. Remember to be in the working directory. And now we can use the LendyDB SQL file to read into our database to create the tables. And this file is included in the zipped file. So let's read this file into our database. We should get those errors. So now the database is ready. We can insert the test data, and you can use the Lendy data-SQL. What it will do, it will read the data into our database. So let's run this file. So I will explain this file. So several things are noteworthy in this script. The first point is that the format of the dates. Although SQLite does not have a date data type, it does have a number of functions that can be used to create standardized date strings and values that it then stores as text, or in some cases as floating point numbers. And the date function used here requires the date string to be in the format shown, and an invalid date string will be stored as null. Using date function therefore improves data quality by ensuring only valid and consistently formatted dates get stored. So when we are inserting the data with this file, the database design now includes some referential constraints when we read the SQL file. So we need to think about the order in which we populate the data. The member data has no references, so it can be loaded first. The item data only references members, so it comes next. Finally, the loan data, this section here, references both members and items, so it must come last. For the data insertion section, we are essentially repeating the same insert operation over and over with the different data values. This time Python is the better solution because we can write the SQL once and execute it many times before using either execute many method of the cursor object, or by calling the execute method from within a Python for loop. So this is how it's done. So have a look at it to understand what's going on. And one note on the dates is that SQLite's use of the date functions to handle date fields is very unusual, but it fits well with SQLite's dynamic typing mechanism. The other date functions include a version of the strftime function that we met in using the time module from section 2. The SQLite version adds some extra features. One point to note about SQLite's time structure is that it always uses UTC, also known as GMT, because this avoids any of the complex issues surrounding time zones and daylight saving time. For display of the data in local time format, you need to use time functions within Python to convert the times returned by SQLite. A page in the SQLite documentation describes how the various date functions can be used in several common scenarios. So check out the the documentation for datefunc function. And the owner ID in SQL this line here, the item owner ID field is specified as not null, so we filled it with a dummy value 0. That is then overwritten by the update code later in the script. Here. And you could have used the for loop to process the insert statements, but instead use the execute many method that takes the statement and the sequence or iterator or generator and repeatedly applies the statement until the iteration is completed. The variable values are inserted into the query strings by using a question mark as a placeholder. This is very similar to the string formatting, using the curly brackets as a place marker. And you may wonder why string formatting was not used to insert the values into the SQL statements. This is because string formatting is vulnerable to security attack known as an injection attack, whereby harmful code can be injected into the SQL statement. Using the SQLite execute mechanism as the formatting tool eliminates this risk because it checks for rogue values. So at this point, you have created the database and populated it with some test data. The next stage is to make the data accessible to applications via an application programming interface. So now we're going to create an API. So creating a Lendy Database API. When defining an API for a database, it's normal to start off by thinking about the basic entries and providing functions to create, read, update, and delete the items. As we have mentioned, this is often known as CRUD interface after initials of the operations. The temptation is to provide these functions as a thin wrapper around the corresponding SQL commands. However, to the application programmer, it is not particularly useful to just be given an ID of a member. For example, it would be much better in most cases to get the member name instead. Otherwise, the programmer must perform multiple reads of the member database to create a useful display for the user. On the other hand, there may be times when an ID is the best option because the programmer may want to get more specific details about the member. The skill in building a good API comes from being able to resolve these contradictions in a way that makes the application programmer effective while retaining full access to the data. Although the CRUD operations are good foundation, it is often more useful to the application programmer if some higher level operations are also available that span entities. To do this, we need to think about how our data is likely to be used in an application. What kinds of questions will the designer want to ask? If you are also the application programmer, this is relatively easy, but if you are providing the database as part of a bigger project, it gets more difficult. For the lending library example with the tool hire example, we focus only on the CRUD interfaces to items and members. The principle should be obvious, and we have the opportunity to extend the API to cover loans if you want to extend the application. And the code is already written, and you can open the lendydata.py file for creating the API, and we will go over this in detail after we have executed it. So let's just go over this module. I have not executed this because we need to work on from the command prompt on this. So in this module, we create two global variables for the database connection and the cursor. The init DB function initializes these variables from here and here. And the same cursor is used in each of the query functions within the module. The close DB function then closes these objects when you finish using the module. This approach means that the init DB, close DB functions must be called to initialize and finalize the database, which adds a little bit of complexity for the user, but it means that the individual queries are much simpler because you do not need to manage the database and cursor objects each time a query is called. Notice too that you set the foreign key pragma in the init DB function to ensure that all the transactions are checked for referential integrity. The query functions all follow the same pattern. SQL query string is created. Let me just scroll up. SQL's query string is created using triple quotes to allow multiple line layouts, and then that string is passed to the cursor.execute method. The retrieved values are passed back where appropriate. The cursor.execute parameter substitution mechanism is used throughout. The two update methods have an extra twist in that they have defaulted input parameters. So the update item, and it should also be update member. So this means that the user can provide only those fields that are changing. The other fields are populated based on the existing values that are retrieved by using the appropriate getDetails function. The two getName functions are provided for the convenience of the user to easily map from the database identifiers returned in the getDetails queries to meaningful names. Typically, the application programmer should use these functions before displaying the results to the end user. And the final section of the module inside the if test is a very basic test function just to check that the connection and the cursor objects are working as expected. It does not comprehensively test all of the API functions, and we will do that in the interpreter now. So remember that you have all these files in the working directory from when you are starting the prompt. Also remember to have all the files in the working directory when you start the interpreter, the Python interpreter, if you are working in the same manner as I'm doing. So remember to have access to Lendy data in the same folder. So we will use the lendydata.py file to insert, read, update, and delete entities from the LendyDB database that we created earlier. We have the Lendy database here. And so first we'll start by importing the Lendy data. That's LD. Initialize the DP. We get all the members. Get all the items. Let's try to insert an item. And the preceding error proves that the referential integrity check works. We need to first add a member and then add a new item. It's added with the ID of 6. So let's try to add the item again. Seemed to have worked. And we have the Python book inserted. Very good. So let's now try to modify the item and member. Let's update it. Let's update the member details. Let's update it. Let's delete. Try to delete member. Again, in the foreign key restriction. And to see how the API can be used for arbitrary queries, let's try these commands. just need to that's a problem. Let's do it a little in some other way so it's more readable. Gets very disorganized when you try to write very long SQL statements, like what I'm trying to do now. I'll try to split it up. Good. Typo. Let's close the database. So, how does this work? So let's start off at the top. So we started by importing the lendydata.py module and assigning a shortener as alias LD. We then initialized the module by calling init DB. We proved that the connection was valid by fetching the list of members and items. We next proceeded to try to add an item. Here, in this part. But the owner ID value was for a non-existent member, and the database foreign keys constraint check prevented the operation from completing. We then added the missing member followed by the item, which this time was successfully added. Having added data, we went on to explore the update functions by modifying the price of the new item and the name of the new member. We also used the getMemberName helper function to verify that the owner ID of 6 was indeed the member of that we had created. And we next try to delete the new member again. Referential integrity checks prevented this because the member was being referenced by an item. And first we needed to delete the item and then the member. So having exercised the high-level functions of the API, we proceeded to use the cursor object directly to execute arbitrary SQL statements. In this case, we found all the items owned by members with an E in their name, followed by all items owned by members without an E. We used the getMemberName function, helper function, to verify that the only such member with an ID of 4 was in fact Rob. Did it here. And I did some typos. And finally, we closed the database, which ensured that all changes were committed and that the connection and cursor objects were properly finalized. So in this section, we have now built a high-level API for application programmers to use, and have seen that by making the underlying cursor object accessible, we enable the user to issue arbitrary low-level SQL commands too. This kind of flexibility is usually appreciated by application programmers, although if they find that they must use SQL extensively, they should request an addition to the functional API. Of course, SQLite is not the only tool available for working with large data volumes, and Python can provide support for these alternatives. So in the next lesson, we're going to look at some alternatives to SQLite and how Python works in this environment. So see you in the next lesson. I hope you enjoyed this one. See you soon.